Okay, welcome back everybody. This is April 1st, April Fool's Day, and today on the menu is the finishing of our Leaky Confined Aquifers lecture. Okay, so again you have the general chapter 5 over there, the Wells hydraulics on the top right, and last time I already introduced a little bit what happens when you're in a semi-confined aquifer or a confined aquifer that has some source term somewhere, some recharge, and we saw a little bit about, we looked at this plot of the new Wells function that has now two arguments. Okay, so this is what you might dream about after that lecture. Well, we saw that confined aquifer, right, the straight line method, excuse me. So we looked at that straight line method for the confined case, so no leakage, and you might think, well, this is not even straight, so why do we call it the straight line method, right? Remember, it's not really straight. The other thing we might remember from last lecture, or dream about, is that the Wells function now has a whole bunch of things in parentheses. So what's up with that, right? And so today we'll basically develop those two ideas, the one of the straight line and the one of the arguments here, and sort of delve a little bit deeper into that leakage, that semi-confined aquifer problem. At the end of the lecture, so we'll do an example sort of manually like we've done for the confined before. And then at the end of the lecture, I will introduce an Excel interface, I guess, that I made that you can use to solve those kinds of problems. So for both the confined and unconfined together. Okay, so again, confined aquifer last time, right? So this is the equation for the drawdown. This is the time function. So this is transient solution for the drawdown. And then it's a function of, time or one of a time. In this case, u is one of a time, right? And you can see you have that straight line and you have that early time where it's not quite linear, but then after some time it becomes linear and stays linear forever. Now the question would be, okay, well, for leaky confined, if there's a leak, right, what happens? And again, we've sort of talked about it already in the previous lectures, but again, conceptually, just to reinforce the point, if we start here close to the piezometric surface, to the original piezometric surface, and now we're pumping into a semi-confined aquifer, right? So there's an aquitard here that is leaving some, this is your well screens down here. All right, so water comes from here. So again, early on, water flows freely, so we have something that looks like a confined aquifer because the influence of the leakage rate, right, doesn't really matter. And this would be your, okay, so your piezometric surface and your well is pumping at Q here. Okay, try and speed that up a bit. Okay, so early on we have the exact same thing as if it was just confined, right? So we have that straight line, so we expect some nonlinear stuff going on. Well, again, when I say nonlinear in the log x case, right? So we expect this thing to be different early on and then to grow as a logarithm of time, linearly in log x for some period, and then eventually, right, the effect of the leakage should start to right, so our drawdown in the well goes down, and eventually there's enough suction or negative pressure, right, that we're equilibrating, if you will, this whole system, right? So the amount of water coming out and the amount of water coming in sort of start equilibrating, so then there's more and more water as there's more and more suction sort of coming through it, right, because the head difference across is higher and higher. So at some point we reach some sort of an equilibrium, and we expect that that drawdown in the well to sort of equilibrate after some time, as opposed to just go on forever like in the confined aquifer. Now, what does that mean? That means that, again, the drawdown is going down, and then eventually we expect it to stabilize somewhere, right? Where that is, well, we'll see. We don't know for now, but that's sort of the expectation. Okay, well, let's look at some model cases here from your book. And indeed, you can see that, okay, again, the confined aquifer is that first case going linearly forever. And again, this is just flipped, right? So on the y-axis here, you have the drawdown, but going down, from 0 down, right, in the well. So it's the same thing, just flipped around. So you can see that nonlinear problem early on, and then that linear trend that goes on forever for a completely confined case with no leakage. And then if you do have leakage, you can see that there is some steady state at some point, basically, that shows up. Now, for this problem of the storage here, don't worry about this for now. The point here is that typically you do have some sort of equilibrium. Of course, if the other aquifer also has some sort of, completely confined problem, so some storage, right? So now you can get into a different sort of linear regime that goes on forever if it's completely confined. Assuming this is a water table aquifer, like an unconfined aquifer, then you do get to that complete equilibrium. And again, I cite Hantush here. You can go back, like he has many of the seminal papers on these problems, and I will put that in your papers folder online. Okay, so this is sort of all models. How about real data, right? So this is actual pumping well data. So drawdown data versus time. Again, time in logs, scale. You can see that linear trend in the middle. So early on, typically we don't have much data early on because, these are short term. So this can be, from, well, depending on the well, I guess, but from under a minute to a few minutes to maybe an hour, but not very long at all. So typically we have data, after the first minute, and that's where your linear scale is. And here you can see that again, we now deviate from our linear trend, that straight line method. So if we deviate from it, this is the telltale that this is actually a leaky confined aquifer, right? There's some leakage going on here. Okay. Now, what does that do to our Wells function? So remember the Wells function from last time I already introduced it. This is what it looks like in log-log scale, right? So you'll remember the top one here, the envelope, is your Theis curve. So that's the one we use for completely confined cases. And now we have that family of curves, right, as your R over B term. So that second argument in that Wells function, now the new argument that we're using for those semi-confined aquifers. So this is the look we're used to. Now, if we semi-log it instead of log-log it, right? So again, this is the log of time, but now this is the regular scale for the drawdown, right? Or for the Wells function. So log for the time axis, regular scale for the y-axis, right? So we transformed it like before. Again, this is the Theis, like that top line here is the Theis curve, right? So it's the envelope here that is now a straight line, right? That's the straight line method. So we could use the straight line method, and now we have a straight line. So everything is consistent, obviously. Now, as we go down, you can see these different curves are actually those different levels, those different drawdown levels that the well will eventually reach, right? So a little bit of leakage, and again, I don't know why this is all jumping around, right? A little bit of leakage will get it very late, but if there's a lot of leakage, right, we can have a very early onset of that equilibrium because there's a ton of water coming from this other aquifer, basically. This is how you read those. Okay, a quick pause, I guess, in this derivation before I jump into the example. So this is an example of a reservoir in Paris, and I'm doing this to just illustrate kind of different aquifers. So this one is actually a reservoir, not an aquifer. But one thing that's known about Paris is those underground galleries, basically, that are all around and under Paris. If you remember when we talked about Darcy, right, we said that his job for a while was actually to be in Paris, responsible for bringing clean water to the cities. And, in the late 19th century, that was sort of an issue, public health issue, because the surface waters were becoming very polluted and unfit to consume, so we were looking at groundwater as a solution, right? And again, this is not one of those. This is actually a built reservoir, meaning the water that you see here is actually coming from about 100 miles away through aqueducts. So it's still like old technology, no pumping, all gravitational force. By the way, there were like horse pumps, back then and even way before that. But anyways, this one is coming from, it's gravity fed basically all the way to Paris as a reservoir. The point here is that there's a lot of galleries under Paris, and this is just a built one, but there's a lot of them that were dug to access the actual aquifers under Paris to, feed the water to the city. Okay, so I do have a question here that you can complete online. You'll see you'll have a multiple choice online. This is more for attendance than anything else. So if this was an aquifer, so if this was actually a gallery, dug under Paris as opposed to a reservoir built, would it be confined, semi-confined, or unconfined? And you'll have a quiz online to answer that, and then an open part to say like why this is confined or unconfined or leaky, right? So there's a multiple choice part and then an open-ended question here. Now that I made a little digression into that Parisian reservoir, I want to start with the example I've been talking about, right? So this is data from a pumping test in a leaky aquifer. The pumping rate was 1,037 cubic meters per day, and the observation well is 128 meters away. Okay. So here I will illustrate first the manual method, so very similar to what we've done for the confined case, the completely confined case, kind of matching, that transparency with the curve and then reading all the necessary information from the plot. And then again, I'll introduce how to do the same with that little MATLAB sort of automated interface. Okay, so again, the well is 1,000 and the other one is 128 meters away. Now this is, once we move those two graphs on top of each other, this is the match, right? You can see that this is a very good match to this curve here, and so this is between the blue and the yellowish. So if we go down from 0 up top, right down the blue and the yellowish, so we're here, so we can see that our argument, or second argument, R over B, the color scale here is, I can't write with my mouse, 0.3. Okay. Now the other thing that okay, so this is here. Now we need to read S and W R over B at U is 1, right? And the reason, well, you can still do a 1-and-1 match point. It doesn't really matter what you do, right? But here I'm just saying it's easier to pick U is 1, so you can see here, U is 1, right? This is our Wells function. You can see here those curves go all the way down, so this is actually 1 over U, right? And this outside axis here is W, right? So if we go to U is 1, so 1 over U is 1, at 1 we put a line here and we go read what S and W are at that point. So this is here, right? So you can see here that S, so this is the inside axis, right? The data axis. S is so this is 0.1, right? This is 1.1, 0.01, so this is 0.1 something. So S equals basically 0.1 and a bit, right? 0.1 something. It's not quite 0.15, but 0.12, 0.13, something like that. And then if we go out to the WU graph, we see this is 0.1, 0.2, so 0.2 something, right? So W equals 0.2 something, 0.25, 0.2, whatever you want to call it, if you're reading manually. Okay, so now we have everything we need, right? We can actually solve or plug into the equations and solve for everything. So again, the matching curve is for B, R over B is 0.3. We've seen that. We read from the graph that S is, well, I picked it slightly different numbers, and again, you've seen a minute why. So S is 0.13, W is 0.23. Now using our equations, right, so S equals blah, 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 we can plug in and find, again, remember Q was 1000, sorry, I didn't put it back on here, but it should have. So Q here is 1037 and R is 128. So once we plug in, Q is 1037, we can, S is 0.13, W is 0.23, so now we have everything except T, right? So we can calculate T as 146 square meter per day, and then using U equals, you know, the usual, we can find the storativity since we know everything, right? Now we know T, R is 128 squared, so again, we can revert everything and find the storativity. With B prime is 10 meters, right? Now we can calculate our leakage rate, which is the square root again of transmissivity that we now know. If we know the thickness, now the only unknown is K prime, right? So we know R over B equals 0.3, right? So we know R, so we can calculate B here and then finally calculate K prime. And that gives us K prime is 0.011 meters per day. Okay, so again, this is the manual way. We match the curves and then we read everything from the graph, we plug into the equations and calculate. Okay, now I want to get into the Excel, my Excel interface, and you will see this is very simple, and this is sort of an intermediate step between this sort of manual method where, you know, you have to go and actually use those curves to match visually and then sort of read everything from the graph, you know, like the ancient way of doing engineering and science, you know, before computers pretty much, and the fully automated, right? So we could automate this whole process to have some sort of minimization of the, you know, squared error type of thing, right? And then the whole computer would do it, and that's sort of what GMS does for you, right? Or those packages, you click a button and then they use those equations, you know, make it all fit and spit out the numbers. So here is sort of the intermediate step in Excel to get to do that. Okay, so let me switch to Excel real quick so I can actually show you in there how to do this. If I can get rid of that, here. Okay, so now we're in Excel, we're in the actual program. And you can see this interface is really simple. And again, this is only for completely confined and leaky aquifers. I will, next week, I will do the unconfined cases, and I have another interface for those. But for now, just to show you how it works, right? So this is some data, the same data as we just used, you know, manually. So you recognize the data, right? So 1037 cubic meters per day. 128 meters was the distance to the observation well. Well, this we don't know yet, so let's say, you know, we wouldn't know, but let's say, you know, or I should say, quotation mark, if I can find it, here. Okay, so the data again is 1037 and 128, that's all you know. Then the actual data, the time and drawdown, right? So that's what's plotted in black here basically for now. So this is the data we just looked at, so we have the data obviously. And then here the trick for this interface is to shift the data. I already, last time I think I did a quick example where, you know, when you know your 1-and-1 matching point, you can sort of, you know, calculate what your relative time and relative drawdown is just by the ratio that you had to move your, right? So when you move your data, that transparency in front of that Wells function, what you're doing is really rescaling your data, right? You're just moving it left and right, up and down. So you're basically multiplying it by sum or dividing it by sum on both axes, right? And this is literally what this is doing, right? So what you have to do now is once you have all the red stuff in, so for now Q and R and then your data obviously, what you want to do here is modify those top two numbers, and this is how the interface works. And then here we have an equation that basically just rescales your data, you know, depending on what those 2 points are. So again, what I recommend is just put 1 here for 1 over u, because again, this is the 1 over time thing. So it's just easier if that stays 1 typically. And then, but that can, you can make it different. Like basically, this is your x-axis and your y-axis. So you're rescaling in left and right from the 1 over u number, right? So let's say I go to 3, right? Shifted right. You can see the data here moving, right? So I shifted left and right. So at 1, looks like I'm pretty good, right here. So I shifted it left. And then the y data, again, you shift it up and down. So here you can see that this curve here, it looks like it could be matched over there. So we want to raise this up. So let's do at 0.4, for example, or whatever. So this is going to be too high, right? Now, if you remember from our manual method, we already read that from the graph, right? But you can see how iteratively manually you can kind of go up and down until you match it, until you find that good value, I guess. Now, we already know what that is because we just did it manually, so we already read it. So if we put 0.23, we're pretty sure we're going to be good, right? This is exactly the data we had in the manual example, right? So here, instead of moving it by hand, we're sort of moving it by, changing those numbers, but it's exactly the same, moving it up and down and left and right with those x and y values. Now we have the match. We can read this green, this matching green curve here, which is, of course, R over B is 0.3. It's the same example, right? Same data, so it should be the same results. Now if I plug 0.3 here, you can see what happened is we now calculated the transmissivity and the storativity. So 146 square meters per day, 1.2 e minus 5 storativity, right? And now if we, okay, so B now is 426, the leakage factor, so 426 meters, that's our B. Now once we have B, well, don't worry about hydraulic resistance. I haven't really talked about this much, the leakance and hydraulic resistance. But the leakage factor here is 426 meters, and this is the expression for it. So now we have everything, right? We have B, we have transmissivity. If we know B prime, so 10 meters here, it's a red cell, right? So if we plug 10, then we can calculate K prime as 0.008, okay, meters per day. And I think that's slightly different from the one I calculated in the manual method, but it's, close enough, I guess. Okay. I will have to recheck that hydraulic conductivity. I don't know why there's a slight difference here. I will check that. Okay, so this is it for today. This is again finish the leaky, the semi-confined aquifers. Showed you the manual way to do it. Showed you the semi-automatic way in Excel sort of way to do it. For today, you will have that multiple choice question to answer, and also an example to use this interface, this Excel interface, this simple Excel interface, so that you can sort of play with it and get familiar with it. And then on Friday, I'm trying to get a live session where we can do similar things to what we used to do in our Friday sessions in the lab computer, but now, of course, from home. So we'll see how that works. But I'll tell you more about it, from the classroom and from other communications. Okay, thanks for your attention, and I'll see you on Friday. Bye.